Hey everyone, welcome back to the dining room table. So it's been a little bit and I decided I should make a video providing some updates on projects. I've got some cool stuff in the mail I'd like to show off and talking a little bit about some projects I might consider working on in the future. This is my first sort of Monday night meatloaf style video, really just odds and ends and things that wouldn't make a whole video, in and of themselves, but I figured you guys might find interesting. So stick around and let's look at some neat stuff here. So real quick before we get into the fun stuff, I thought I should provide a brief update on the diamond turning lathe and where that's at. After I graduated, I moved to a different state for my new job, and unfortunately the lathe hasn't come with me yet. Yet is the key word. I'm planning on going back and getting it around the holidays in December and bringing it up here with me to live for now in my apartment here. I'll keep working on it. I've got some fun stuff planned for it. We've got some software upgrades regarding cam and error compensation. I plan to do a full geometrical error characterization of the whole machine using a reference standard, which I'll show in a second here. And then hopefully integrate the interferometry feedback with the cam system for sort of a closed loop process for turning really high precision stuff. So it's not here, it's coming here, and we're gonna keep working on it and keep making some cool shiny stuff on it. So stick around for that. I know that's what a decent amount of you are here for, so I figured I should mention it and not disregard it completely. But so jumping off that, how am I actually going to characterize the errors of my machine and compensate for it? Well, I think modern standards would say, put an interferometer on it, put an autocollimator on it, measure the straightness of all your finished axes, and then you can go from there. But it's still perfectly valid to do it the old-fashioned way, where you simply compare it to a reference or a standard, something that's much more straight or much more accurate than your axis you're trying to measure. So I've shown this before. This is my optical flat I've had for several years. Just a fused silica flat with lambda over 20 flatness. So micro-inch or so, very good. Got something in the mail. Oh yeah. Take a look at that size comparison there. So very nice internet stranger sent me this, but this is a 14-inch optical flat. It's not, it wasn't made for the purpose of inspecting flatness necessarily, but it happens to be an enormous, 2-inch thick piece of silica, which is flat, not to lambda over 20 over the whole surface, but locally, like over this 3-inch distance, lambda over 20. So that comes out to, I think, lambda over 4 over the whole surface, which is, more than good enough for what I'd like to do with it. And it's, it's a very flat surface, so I can run an indicator along it while that indicator is fixed to my diamond turning lathe axes. And yeah, it's a bit of a pain because it's so big and bulky, and there'll be some weird setups involved, but with enough of these measurements, I can pretty well characterize how straight my axes are and build an error map and compensate for that in software. So, I mean, this is just awesome. You've got other ideas for it, like a giant Piezo interferometer and these sorts of things for inspecting flatness, but yeah, shout out to the guy who sent it, and can't wait to use this for all sorts of fun stuff in the future. Next up, we got some more doodads another friendly internet person sent me. So this is kind of a neat one. It's a little 2-axis piezo nano positioning stage. It's flexure based. So each of these two halves here are one axis, and you can sort of see the flexures cut into the body of it here. And inside there's a little piezo stack. It's at a slight angle, so when it grows a tiny bit, you get a motion amplification from these flexures. And so this one moves this way, and this one moves up and down this way here. Just to do a quick test, I've got it set up on very jankily on this little optical breadboard scrap I've got here. And we're looking at the motion of this axis, this in and out one. I've got it hooked up to a power supply, and I don't have a high voltage piezo driver power supply. So the most I can make is 40 volts DC that I can drive this piezo with. I'm sure it could take more, but let's look at what 40 volts does with it. Okay, so we'll zero out our millimesh here. Get it as close to zero as possible. That's good enough. And I'm just gonna reach back here to the power supply, and we're at 0 volts right now, and we'll ramp it up to a full 40 volts. And there, that's actually 46 volts is what we're maxed out at. So yeah, about 1.5 tenths is the travel we get per 40 volts. And in theory, that 1.5 tenths, that travel is, very free of, stiction and hysteresis and all that jazz. Well, there will be a little hysteresis technically, but extremely smooth motion over that range. I mean, you can see the needle moving up and down, and that's me sweeping through a huge range on the power supply. Even just on the power supply here, I have 10 millivolt control over the voltage. So you can imagine how small of a displacement we can make with this. I think to really utilize it best, I would, actually build a real piezo driver and maybe even have some sort of feedback integrated into it. But yeah, really neat little stage here, and I don't have, a great idea of what I can do with it right now, but surely something, maybe like maybe even a fast tool servo system or something like that, because our range is very limited. We don't have a bunch of range, but you can realize decently high bandwidths and just absolutely crazy small precision adjustment with this. So come up with something to do with it. So this one's really fun. It's a little nano positioning stage, not unlike the other one, piezo based. This one's got a much longer travel though because it works differently. But these are just the plugs, right? Now, have you ever seen a linear motion stage smaller than the plugs to interface with it? I mean, this is just absolutely cute as can be. So this is a cool little stage here. You can see it's on 2 micro linear rails. Most of the size here is this guy. It's got a glass scale, exposed glass scale encoder, Micro E brand for feedback. And then the drive, you can see down in there, I think this is one of those piezo stick slip drives. So there's on the base here, there's a piezo element, and then on the moving part of the stage, there's a ceramic strip you can see there. And I can actually overpower. It's not good for it, but I won't do that a lot. And yeah, there's the strip that the little piezo actuator actuates on. So it's, it grows slowly and then jumps back and slips and pushes, basically inches the stage along that way as a way to think of it. And there you can see the glass scale. So, I mean, that's just super, super cute there. I really like this a lot. I've played around a little with trying to hook the encoder up. This is the encoder interface box here. It's so bulky like this because it's also got all the interpolation electronics and everything in there as well. But I've not been able to figure out what resolution it is yet. I do need to measure that. And then this one's a little bit harder to actually drive because of the nature of the drive. It's not just as simple as applying a voltage. You actually need to build a high voltage driver that applies the correct waveform. That's the trapezoidal waveform to move this thing. So that'll take a little more work, but I mean, I can't get over how small this thing is. It's awesome. So, and last thing from this batch of fun stuff from a stranger is this guy. This is an STM, scanning tunneling microscope. These are the things a lot of times whenever you see photos of atoms online, they're taken with an STM, and photos in quotes, but images of atoms. There's not a lot of things that can do that, but STMs are one of those instruments. And it's, I've always been very impressed by those photos, but I've never really understood just how simple they were. So this is basically it. The way that works is this here is the needle holder, and there's a very, very sharp tungsten needle that you would put in there. And when I say very sharp, I mean basically as sharp as you can physically make anything in the universe, because we need it to terminate down to almost an atomic tip. And that's on this tubular structure here. And that's a little piezo tube actuator. So that's a little cylinder of PZT material with electrodes placed on, 4 different quadrants of it. So if you were to apply a voltage potential just on this side, over the top and bottom, this side would tend to grow, whereas this side didn't do anything. And you could basically bend the tube by applying strains to different parts of the tube. You have a bending action that occurs. And so with that, you can sort of wiggle the needle in, 2 different axes. And that sort of approximates a linear translation over these extremely tiny distances that we're moving here. And then all the rest of it is we're monitoring the tunneling current between that needle and the sample that we're looking at. So this is a preamp that sits on top here, and then there's a bunch of other signal processing that needs to be done, and amplification as well. And then the rest of it, it's really just this kinematic mount where you hold the sample with this clip here, pull this out, and you've got these 2 manual adjustment knobs to adjust the height and level of the stage there. And then this third one interfaces with a coupling in here, which goes down to a stepper motor in the base. And that's what we can use for our final height adjustment to bring the needle down onto the sample, since these are super fine pitch screws there. And it's a kinematic Kelvin coupling arrangement. We can just slap it on like that, and there's our STM. So this one it'll take a while to get working, because I've got to build literally every other part of the electronics and driving circuits and all that stuff. I know there's some open source STMs out there, so I could probably reuse a lot of the stuff from those projects, but this one might be a cool one to get working. I just need to find a way to either make my own or afford the needles. So thanks again to the last guy who sent me those last 3 atoms you saw there. Really great stuff. Now real quick, this is a little tool making project that I did a while ago but kind of forgot to show. I kind of wanted an indicating micrometer, but sort of purpose built for some more high precision stuff that I'd like to use it for. And so I made my own. I've got a clip on Instagram where I actually am sawing this nice brown and sharp micrometer right in half in 2 to really make some people mad there. But I wasn't using this 1 to 2 inch micrometer very often, and I thought I could repurpose it into something a little more applicable. So I did. This part that I added here is real simple. You can see how this interfaces with the old micrometer there. And then we've got a little clamp system up here. I've got my adapter sleeve in it because this is designed to take either 3/8 shank stuff, like some LVDTs that I have are 3/8, but then also the 8mm of our metric metrology friends, like the Millimeter here. So there's a few different things that this is useful for. The main thing I made it for actually was quickly checking taper on the cylindrical grinder. So when you have a cylindrical grinding set up between centers, you need to align your centers with respect to the axis that you're traversing on, so you don't grind a tapered part. And this is a quick and easy way to check that taper. So you can imagine, hang the anvil on the top of the part and swing this indicator underneath, sweep, look for the high spot, and you can basically get an idea of your taper within a half a micron pretty quickly and with a nice precision feel. But you also have the micrometer aspect of it and the whole measuring aspect of it. So beyond just comparative measurements like checking taper from one end of a part to the other, you can also set and zero this on a gauge block or some sort of gauge, and then check your part, and it's still a comparative measurement, but now you're actually inspecting an absolute dimension. So again, that's more for diameter stuff. You can also use it on flat stuff. It's really more of, it gets a little more tricky trying to get it seated on this one anvil well, but useful for that. And if you don't need crazy precision, but just the convenience of an indicating anvil, you can zero it on a gauge block, but then if you need to go to another dimension, you can use this like a normal micrometer and just set it to whatever dimension that you'd like to inspect, lock it down, and then basically real quickly check and watch yourself creep up on a dimension. And it's just way easier than measuring and reading the micrometer out and then saying, okay, we've got this far to go. It's just the convenience of an analog needle display like that I'm a fan of, just from a workflow standpoint. So it was a fun little project to make, and comes in handy for a few applications. And it was a nice lesson of the old Renzettiism. Don't be afraid to modify your tools to make something else out of them. So yeah, thought some people might find that one interesting. All right, so second to last here, we've got a cool score from eBay. This is a Parker MX series linear cross roller bearing linear stage. It's got a linear motor inside of it and a Renishaw encoder going through a Renishaw REE 2000 interpolator, which gives us a feedback resolution of 10 nanometers, so not too shabby at all. Granted, it's interpolating 2000x from a 20 micron encoder, so it's not a super reliable 10 nanometers, like not exactly 10 each time, but still very high resolution, really neat. I've got it hooked up to one of the Ioni servo drives that I have spare, which is why you can hear it making some noise here. It's because it's currently under active servo control. I don't have a tremendous tune on the servo right now, but that noise I'm thinking is not necessarily just a result of jitter from a too tight of a servo loop, but it's actually because of noise from the encoder signal itself. Interpolating a 20 micron encoder 2000x doesn't exactly yield a clean, really stable output. There's a lot of electrical noise that gets converted into steps, or what it thinks are steps, and the servo loop is trying to compensate for that and keep up with it, and so you get an audible noise sort of constantly. And I've tried a wide range of servo parameters, everything from very tight to very loose, and that noise is there, unless I have a pretty restrictive filter, bandpass filter on the control loop. So I think it's just inherent to the noise coming from the interpolator electronics, but it's no trouble. It's not a large noise floor. It's within a couple encoder counts. And let's take a look at some movements here. So I can bring the camera in so we can look at the millimeter. We're using that as our standard for all measurements here at Silos Garage. Not really, but here I'll take some large macro moves. I don't have the speed set super high right now, so these are about 2.5 millimeter steps here. Take some larger steps. bang, come back to 0. Pretty impressive. You can see that sort of ring down when we come to our position there. Just again, because the servo tune is not necessarily ideal, but it's always satisfying seeing it come back to 0 like that. And of course we can make some real small steps too. So from here, I'll set our step increment size to be 1/10, for example. And there's some 1/10 steps there. Those are not quite as noisy as you can hear. And you can see we're not gone off scale there. It's not it's not perfect. 1/10 steps repeats to 0 decently. I'll come down a little more accurate on this side. Could be flexibility in the metrology loop, could be, a lot of things. Also could be my millimeter is not perfectly in calibration. It's very, very likely. But it also could be that, again, we're, there's a lot of interpolation going on here on this side of the feedback electronics, so you get some subdivisional errors there. And we can make those steps even smaller. Let's reduce it by a factor of 10 or so. And so there's some approximately 10 millionth steps. It's actually, there's a rounding error. I can't go this small because of the way I have the servo set up. I can't reduce exactly by a factor of 10. But this is, let's see, 250 nanometer steps. Pretty small. Heck, we can go even smaller here. There are some proper 100 nanometer steps. And it is responding. And we can go back as well. No backlash there to speak of. Pretty cool stuff. So, yeah, I mean, it's a neat stage. I don't know what I'll do with it, as with many of the things in this video, but I'm sure I can find a fun project to put it on. But, never gonna pass up an opportunity to show the millimeter moving in small increments with, a very satisfying level of repeatability. Fun stuff. And finally, we'll wrap up with a couple more mailbag items related to more. This is just ultra nerdy stuff and generally fanboy behavior, so we've saved it for last. First up are these guys. They're just little setup blocks that another friendly internet person sent. I've not measured these to see how accurate they are, but I would assume they're pretty good. And these are the first things manufactured by Moore that I own, so fun stuff. Look forward to using them. The real star of the show comes to me by way of the homie Lewis from Minnesota. And, well, it's a scraper. It's a hand scraper, and this is good. I had a Sandvik one at one point in time, but I've actually lost it, so happy to have a scraper again. As you can see, it's been well used and well loved, but what's special about this scraper? Let's look at this side. Got it upside down here. What do we have on there? MST Co. JB Div. So, in case you've not deciphered the code there, that's Moore Special Tool Company, Jig Bore Division. So this is actually a scraper that came out of Moore, specifically the Jig Bore Division, and was used by, employees of the Moore Company to make the jig bores. So not only is this a real high quality Anderson scraper, this is straight out of the Moore factory. And that's just, you know, the coolest thing, as, you know, someone who's a fan of Moore. You know, this scraper was used to make some of the most accurate machines ever made. And I just, you know, appreciate that to the fullest extent possible. So really cool piece of, I would say, history here. Niche machining history, yes, but piece of history nonetheless. Very, very grateful to have it here with me. Thanks again to Lewis. And I look forward to using it one day on a project, and hopefully I'll be worthy to wield it to its full potential. So cool stuff. And thank you again to everyone who sent stuff my way in my little period of silence here. It's been a lot of things going on as I've moved and started a new job and everything, but looking forward to getting that lathe back up here and getting back to work on it, making some cool stuff, and you know, making some cool stuff with these new toys that I've got. So I'm thinking, you know, white light interferometer is on the table, Piezo interferometer, a couple other metrology based things. Got some fun stuff coming down the pipeline, and maybe one day I'll even get to show what I get to work on at work, so that'll be exciting too. Until then, hope you guys enjoyed. Thanks for watching.